Okay, I hope you can hear me. Welcome to my talk. I'm pretty amazed that so many people are interested in what I'm talking about. I hope the quality is good enough so that that you actually get what you paid for. Now I'm going to start it. This is a short overview of what I'm going to talk about. It's a little bit an introductory session on how data recovery labs work from beginning to end. So I will have a little look on the process, then I will show you a little bit about the lab setup, how it looks like, and what you actually need and what you don't need. And yeah, and then this is mainly about what's data recovery all about. It starts with the physical acquisition from a damaged storage media, or maybe sometimes from an undamaged storage media, but it always starts with the physical acquisition of the data. Then we have another abstraction layer in many cases. That is, if you combine many storage media together into a disk array or something like that, into a RAID or whatever, it adds another abstraction layer. And the next one will be if you export that to a storage area network or for instance, via iSCSI. An iSCSI target is practically a file on another machine, and that represents it represents to the iSCSI initiator as if it's a disk, but in fact it's not. It's a file that can even be fragmented on some other server somewhere, or on a SAN or NAS or whatever. Yeah, the next complexity thing is virtualization, meaning that many data are not accessed by real machines, but rather by virtual machines, meaning instances where operating systems run in, well, you all know virtual machines. The next step is file systems. If you have this media or this simulated media or this iSCSI target, then it's usually partitioned or whatever, and then you find one or more file systems on it, which is the next layer of abstraction. And then it comes to file formats, which is extremely important, for instance, if you're running a database. Because a database, again, is sort of a file system, meaning the records are not stored one after the other in the database, but it has a controlling structure that says which record is in which block, and it keeps track of those blocks by itself, by the storage engine. So you can see there's a lot of abstraction from the block that you grab from the actual drive until the record that you can present to your customer. Here is your data from the database. Yeah, of course you need to verify the result, meaning you need to be able to predict if this file is working for the customer or not, and that you have to do automatically somehow. And I will go more into detail about that later, how you can do that easily. Because if you are taking data together from damaged hard drives, you are missing blocks. I mean, you are certainly, but if you're not missing blocks, then you probably don't need a data recovery. Well, in most cases. In most cases, you are missing parts of the data. So your view of the world is sparse. But how do you tell if this record of the customer is there or not? How do you judge that? But we start, of course, at the beginning. Well, first thing is, many companies have videos of people running around in full bodysuits. That's, of course, nonsense. What you need is, you need clean atmosphere. Most of dust in our business is introduced by the customer drive itself. It is not from the surrounding air. So the first step is always to clean the media you're getting in prior to analyzing it. Because when you open a dusty cover from a hard drive, of course the dust goes into the hard drive. Then you need a little bit of microscopy. I will later on show pictures from the microscope, because sometimes alignment of heads is very critical, meaning that you need a video microscope to adjust the heads to for their correct position on the head arms. Anyway. It's always good to buy best tool quality. I can't say that often enough. Many people are buying bad tools. No tools are better than bad tools. In this business, we're using standard tools, and we're using, of course, specially machined, specially crafted tools, because they're not available on the market. Yeah. Then what else do you need? Lots of computers. You need some disk arrays to store the images on and to store the final extracted data on. That's pretty obvious. Well, all kinds of adapters and cables, and a shitload of disks for two reasons. One reason is, some cases, you need one-to-one copies to physical disks. Therefore, you need a lot of disks. And the second reason is you need spare parts. And I think there are probably, by today, there are more than estimated 10,000 drive models out on the market. Meaning, if you these drives are, or the spare parts are not interchangeable between drives. Sometimes they are interchangeable in a series, but sometimes they are even not interchangeable in the same model. And that's, well, we've got a huge database of which spare parts fit into which model. And yeah, sometimes it's not even, if the model number matches, you got two drives and they look exactly the same, and they have exactly the same numbers on it, it could be something completely different inside. And the hard drive manufacturers, well, there's a reason for it. For instance, if, let's say, company A orders 1,080 gigabyte hard drives, and now they got 200,000 already, but now there's the next generation of hard drives coming, but the contract is on that specific model. So what does the hard drive manufacturer do? Runs the factory with legacy technology? No. He will just put the same label on a different hard drive. And sometimes these hard drives even have more capacity than it's printed on the label, so they are just scaled down by the firmware so that they have exactly the right number of blocks that has been negotiated with the customer. So what you see on the right side here is a set of heads installed in a video microscope for alignment. We will see the picture later on. It's just a... Now, this is how we are doing the clean air. It's a German company actually that builds these boxes. I see, well, we are still missing something of the picture on the right side, but I think we don't care for this talk. Well, these are boxes with very good filters and with a laminar flow from top to bottom, meaning that there is a pressure inside of the box that pushes out the clean air to both sides. So that's why it's open in the back also, so that the laminar flow can go to both sides, to the front and the back. Oh, I'm very sorry. Now, some examples of tools. In the upper left corner, it's a standard tool. It's a chip reader for flash chips, standard flash chips, which has a USB connection. You can buy it on the market pretty easily. That's standard technology. You want to, if it comes to whatever flash media, you want to read the chips, right? That's what you use it for. Top right, you have something we call a head lifter. That's a standard, that's a specifically machined tool that we did by ourselves. And we have some software that does it by parameters taken from the measurements, from the dimensions of the hard drive. So we're disassembling the hard drive, then we're doing the dimensions of the hard drive, feed that into a program, and that gives us the proper head lifter for the specific hard drive. And that's what comes out of the process. The material is polyoxymethylene. Here, this picture shows actually, looks a little bit like a bar. That's actually to extract the platter hub from the spindle bearing. That is necessary once the bearing gets stuck and you cannot disassemble the platter stack due to accuracy constraints, then you have to take off the whole platter stack at once. And that is the tool, that is one tool for one specific hard drive to do that. On the left-hand side, you see exactly the opposite. That is a press that actually puts it back onto a new spindle. So this is to press in the bearings and to press the platter hub, to press the platter hub back into a shell, or to press the bearing back into a shell, and then the platter hub onto the spindle bearing. Now, of course, there is some logical work also, and this is one example setup of a job. That's what this job is currently, what it's about is we can see on the left-hand side, we can see some, I think some 16 terabytes in the drives on top of that little storage box. And it's actually a RAID job where it's practically goes from left to right. On the right-hand side, you got the fiber channel RAIDs that actually take the data, which are to be extracted from the left-hand side with one intermediate step to a 16 terabyte RAID. And it all happens on this workplace. Just as an example how it looks like. And here you see my office chair. Is that one. And well, and all you see, I regularly have some logical work around me also. Now, how are you approaching a disk and how are you approaching a flash media? I'm starting with the disk. It is crucial that you can spin the disk in its own shell or in a replacement shell due to speed constraints. Any other method is usually commercially not viable because it just takes too long. At current hard drive capacities, there is no way to get a raw image within less than a month other than spinning the drive inside its original or a replacement shell. So in 99% of the cases, we will have to do that. Of course, you can manipulate that shell and you can manipulate any part of the hard drive to tweak it so that it will give you the data. A method that we have explored in the 90s was spin stands. The company I was working for has done a complete, where I was working for in the 90s, has done a complete spin stand and has done a complete reverse engineering of a drive at the time and reading it via an air-bearing spin stand. But I can tell you, today it is almost impossible to get the platter centered on the spin stand so that you can accurately read it from the spin stand without evaluating the servo information. So spin stands today are only for engineering purposes. They are not used, to the best of my knowledge, for data recovery purposes. And the last resort actually is the MFM, the magnetic force microscope, that can take images from a piece of a platter as small as, let's say, 10 microns in a square. So if you are using the hammer and destroying all the platters, that will not be good enough against the microscope approach. The downside of the MFMs is that it takes quite a lot of time to read one surface. I would estimate about 5 years. I mean, if you're not the NSA and money doesn't matter, because then you can have as many instruments as you like. Good. Now, what is the, I think I skipped the flash, sorry. That shouldn't happen. Well, the easiest damage is a PCB or a circuitry damage, and that, of course, can be repaired to get the data out. But I tell you from my experience that it doesn't happen very often. Well, if that doesn't give you the data back, then you have to desolder the chips. Then you have to read them, and then the adventure of bringing the blocks back into their original order begins. Okay, what is the damages that can happen to both of these media? Obviously, the disk suffers a lot from surface damages. Then, if you drop a drive, in many cases, you will bend the spindle, meaning that it won't turn anymore. If the spindle is bent inside the bearing, then the complete platter stack is a little bit slanted and it's stuck. And it's so stuck that there is no tool that you can make it move again. Of course, read-write heads can be defective. And if the heads have not been parked in the designated parking zone, or they have not been moved to the ramps, some of the drives park the heads inside in an area where they use CO2 lasers to avoid the stiction. So they punch little craters in the inner media zone so that the heads cannot stick to the surface. But for instance, if you move a drive and you knock it somewhere against something, then the heads could either fall off the parking ramp or fall out of the parking zone, and then they will, in most cases, immediately be stuck to the surface just from adhesive force, and you won't get them off live. Then we have some electronics failures, firmware corruptions. That is pretty common in the last couple of months or years. In most cases, you don't see anything wrong, but the drive just doesn't respond on the bus. That is a high probability for a firmware corruption. Media contamination, meaning that, for instance, bearing fluid comes out of the bearing and and spills over the platter, then of course you're done. Yeah, and then you've got all these external impacts like fire, water, and shock. But shock usually leads to surface damages or stiction or whatever. But you still have fire and water impact. Many people think that hard drives are sealed, that there is no air exchange between the hard, or even evacuated. But that's nonsense, because the heads actually are flying on air. So the hard drive needs the air in order to work. And so actually there are little holes in the hard drives that allow the pressure to even out between outside and inside of the shell. So water can, in fact, if you drop a hard drive into the water will, in fact, pass those holes and get into the mechanism. Okay. Well, on the flash side, it's pretty much the same, except that we have no mechanical components, that we have no rotating platters and heads and stuff. But of course, almost the same can happen to flash media. Now I have some pictures of these. Yeah, it's a nice mark. It looks like a little man with a nose, but it's not. In fact, it's where the heads. This is actually a dropped hard drive, and that's what we call spots. It's when you drop the hard drive and the heads in their springs go up and down, and they knock on the surface. Then they have sort of grooves in the surface, which will in turn destroy the next head you will try to fly over the surface, unless you take special measures. Anyway, this is a circular crash on a hard drive with glass platters. This is, unfortunately, it doesn't look so bad, but this one is fatal. And there's two reasons for it. One reason is the crash is in the area where the hard drive specific firmware parameters are, so you can't read them anymore. And the second is, maybe, I'm not sure if you can see it correctly on the photograph, but these is glass platters. And once the head is down to the substrate, then it will create glass particles inside the hard drive. And it doesn't take very long until you haven't any surface left. Yeah, it's like sandpaper, basically. This is an obviously fatal one. You can see 3 heads lying on the surface down there. I mean, what used to be the surface. Because what you are seeing here, this drive or these platters were made from aluminium. And what you see is the aluminium substrate. There is not any magnetic thingy on this platter anymore, except maybe in the outer rim there. Yeah, that one is a nice one. And you can see, I mean, in that case, you don't need any dust-free environment anymore, because I think it's more likely that this drive will spoil your dust-free environment than vice versa. Huh? It was a little crash, and this is a large SCSI hard drive rotating very fast, and it took them too long to realize that this hard drive was broken, so it ran for a couple of days. Yeah, it was part of a disk array, and they didn't realize. And yeah, and when they realized, we couldn't do anything for this drive anymore. The other drives were different, but this one was definitely not worth trying. I told something before about stiction. Now, if somebody tries to turn the platter with the heads glued to the surface, stuck to the surface, then it will look like that afterwards, because the head will still stay on the surface, and if you apply a rotating force to the surface, it flips up the head, and in this case, I don't know if you can see it badly. In this case, the spring from the heads went down to the surface and did a scratch there. So if the drive is stuck, don't turn it. That's actually my desktop background, because I just liked it because it was so beautiful. There was, I mean, this is not very exciting. It was just a couple of burned components on the PCB, and I didn't have an SMD diode, so I used another one, as you can see. That was just a PCB repair. Okay. Now we start to look a bit how the heads look like. Here we have a read-write head of a hard drive, a damaged one. I think you can see it there. It's pretty dirty. And this little triangle on the right side, that tells you where the actual sensor is. We are looking from the flat side, from the side that actually flies over the surface to a slider. And this black thing that you can see with your bare eyes is not the head, actually, it's a slider. And the head is on the front side of it, rotated by 90 degrees on the front side of it. That's where the leads come in. Now, yes. I said something earlier about head alignment. For some hard drives, it's completely, they completely don't care about how the heads are aligned, but others need a very precise alignment of the heads. Otherwise, they fall off servo when you switch heads. Well, maybe I have to tell, in a hard drive with more than one head, there's always only one head actually activated and connected to the preamp. The preamp is the preamplifier, which amplifies the head signal from the MR read element. And that actually gets, by a little interface, gets set the number of the head it is supposed to select. And there is always only one head selected at a time in a hard drive, meaning when you read, let's say, the top surface and you're going down to the bottom surface of the first platter, then you have to switch heads. And of course, when you switch heads, then you have to find the servo on the new surface again, that you know where you are. And in some hard drives, I have no idea why, but in some hard drives in the firmware, if you are offset too much from what it thinks where it's supposed to end up when switching heads, then it falls off and gives up. I haven't found the reason so far why it is like that. Okay, so the only approach, I mean, the only thing we can do about it is adjust the heads to what it thinks where they should be, where it thinks where they should be. And yeah, that's a pretty difficult job because they are very small and these offsets are obviously much less than a millimeter. But here you can, now this photograph is taken from two heads, both sliders from the surface side touching each other, and the photograph is taken from the top. So now you are actually seeing the part that is active in the head. You can see a little coil on each head. It's two heads together. You can see those traces, those electric connections, and you can see at least 4 electric connections. Actually, the read and the write element are not one, it's 2 elements. First you've got the MR element to read, and on top of that you usually have a thin film coil that actually writes the data, that writes the transition to the media. And you can see it very nicely, well, maybe in the next picture. I go to the next picture. You can see it very nicely here. That is actually the write coil. And I have marked the write gap where it actually writes the transitions to the media. And behind that, the black thing, that is the read element. And you can see it has 3 leads on the read element and 2 leads on the write element. And the 3 leads on the read element is just that it uses a reference element to compare the resistance of the MR element to a reference. Yeah, I think we've heard enough about heads.
What's the scale of?
Holy crap.
Okay, repeat the question, please. What the fan was.
Please repeat the question to the microphone.
Okay. No, we keep we'll leave the questions for the end, I think. Well, I can tell you what the question was. The question was the scale of this photograph, and I don't know it exactly. So it's maybe about 1,000. This is a fluid dynamic bearing from the inside. I would say 99% of all hard drives are using fluid dynamic bearings in the spindle because ball bearings and other types introduce too much noise into the mechanical system. And this is the bearing dismantled, and you can see the platter hub on top. And the green line tells you how these pieces go together. And the red line tells you this one, even if you can't see it on the photograph, but I can tell you from measuring it, it's a bent spindle. And the bent spindle goes into the bearing case, and it's stuck there, and you won't be able to turn the hard drive ever again. So yeah, and I took it apart to look to see what the problem is. I mean, I took it apart to find out if it's maybe if it died by friction or if it died by bending it. This one died by bending it. So there was too much acceleration force on the platter hub, and that bent this spindle pin, and that made the bearing stuck. So this is a typical drop damage. On this side, on my slide, it says typical drop damage on this one. So you just imagine that, right? I think you can see here that it used to be a hard drive. By the way, this was actually not such a big problem. It was not too difficult to recover this thing. We had more difficult cases. But this is how it looks like when the drives come in from sites where there has been fire, and just to show you how it would look like when it enters the lab. And I have another one which has been through all the cleaning already. That has been a fire damage as well. So how do we know that? Now, if you think it's a 2.5-inch drive, now if you put that in your mind, upside down the drive, and you heat it, then you will see why this has been a fire damage. Because the head ramp, the parking ramp of the head actually has, well, in this photograph, because it's the wrong way around, has been flown to the top. And actually that must have been the bottom when the drive was heated. Because you can see that the plastic followed the gravitation force. Yeah. And this looks perfectly clean, the drive. So you can imagine what amount of work is between having this drive in your clean room from the picture before. This actually has been 100% recovered. Now, sometimes it's very difficult to see what happened. Sometimes sometimes you don't really know what's going on, because everything seems to be fine, but still the drive can't get any servo. And in that case, you can actually use another microscopy method, which is you apply a ferrofluid to the surface and use a light microscope, and then you cannot see the individual transitions, but you will see some patterns. For instance, the dark lines you see here is actually servo bursts, because the servo bursts, well, maybe I have to explain what it is. The servo bursts are marks on the hard drive to tell the heads where they are. And they are usually stronger than the data transitions, the transitions that are written, that are writing data sectors. So you can actually distinguish data from servo. What you can see here very nicely, in the upper quarter, there's a horizontal line. And this horizontal line actually separates two media zones. Hard drives write more sectors to the outer areas than they do to the inner areas. But they don't do it on a track-by-track basis. They do it after a couple of hundred tracks. They increase or reduce the density. They increase it when they go to the outside, and they decrease it when they go to the inside, because there is less area to write data on, and consequently you can't apply the same density. I mean, the optimal writing is if you adjust the density to the linear speed of the media. Yeah. Now, as I told you before about the last resort, this is actually an MFM image well, you can see it's not a 100% modern hard drive. I think it was an 80 gig, 2.5 inch. And there you can actually see the magnetic transitions on the media. And you can see here we have the range. It's 1 micron by 1 micron. And you see on this drive you have 3 tracks on a micron. Because you can, I mean, the tracks are horizontal, almost horizontal. And those vertical bars are the actual transitions, the magnetic transitions written to the media. And that picture has been taken with a Vico dimension MFM. One problem with MFM images, I mean, well, maybe it's too esoteric. One problem with MFM images is that what you see on an MFM image is the actual written magnetic transition, and that has nothing to do with the readback signal you get from an MR head, because these transitions are so close together that your MR head gives you back a narrowed signal that goes over 3 or 5 transitions, and you use math to separate them. So if you apply the usual read channel algorithm to this picture, you won't get the data back. But anyway, yeah, that's probably too. Yeah. What do you think this is? That's exactly, that's an SSD drive. It's a solid state drive. You can see it easily. You got a whole lot of flash chips. They continue on the other side, on the back side of the board. You've got the controller, which is a complete computer, and you've got the cache RAM chip here that is necessary to quickly do the blocking, because of course a flash drive can't write any bit it gets. It has to aggregate a page before it writes it back into the memory, because otherwise it would wear the memory too much. Anyway. This is the inside of a USB chip, not very exciting, but you can see they are using almost exactly the same chips. Yeah. Well, this is the security by obscurity type of protected USB stick, and it adds some more work until you can read the chip, because they are molten in some stuff, and you have to take the chips out until you can get to the leads, and then you have to clean them until you can get them into the reader. But finally, of course, we're reading them. Another thing I was talking about in the beginning is, how do we make sure that we know that this customer file is not damaged by missing raw data? And this is the answer. The answer is, all the blocks that have not been read are pre-assigned with a pattern. And this pattern contains the block number, actually, where the missing data supposed to be on the original media. So if you find this block inside a file, and I mean, I don't need to tell you how to do that, then you know I'm missing this block. This is block number 0. You can see a human readable 0 in the 3rd row there, or 4th, and a human readable 1 there. And there's a lot of more information in this beginning block. But this is the means where you can detect in the end, in the file, in the user file, if it contains block that has not been able to read from the original media, whatever that might have been. I mean, let's say in a disk array, it could be any drive, any sector, and this pattern will tell you where to search for the data if you need it urgently. Now we have only 15 minutes left, so we go to the fun part. It's the firmware part. Well, take particular note of the second drive that has been connected to the computer, and the model name is hacked by CCC. It used to be a Seagate. For this part, we need a warning. Your disk, well, it's said that we are missing a little bit here, but I can read it for you. Your disk will eventually get bricked. So never play with the firmware on data drives. You will lose them. I can guarantee that. It's very easy to brick a drive if you use the out-of-band interfaces and talk to the firmware. Do try this at home, because that's the reason why I'm doing this presentation, to get more people into hard drive reverse engineering and playing. And yeah, the signals are 3.3 volts, and I have to read that for you as well. Commands are different across families, meaning I will give you now a little list of commands that you can talk to the hard drive, but they are only working for the Seagate 7200.10 hard drives. Any other family will have different commands, and even a command that is working on this hard drive can can damage another Seagate hard drive, which is only slightly different from that. So watch out when using them. And again, I don't read it again. You will brick your hard drives if you try it. But anyway, it's worth trying. Well, this is just for reference. If somebody is reading this later on, they can see which pins to connect at the hard drive. I have it as a little photograph here. This is for the serial data. Many people have probably thought, what are these pins where they sometimes have the jumpers on? Well, it's not just jumpers. In most hard drives, you've got a serial interface where you can talk to the controller. And I have put some arrows here on the cable so you can easily see which one is transmit and which one is receive. And the other one is just ground. And it's 3.3 volt signals. And what I'm going to try now to connect a drive and demonstrate how you talk to the hard drive. Because I think I wrote in the announcement of this talk that I will enable you to change the serial number of your hard drive to your girlfriend's name. So give me 2 minutes, I'll try to connect this. Well, I'm using a USB to serial console, which I just have harvested from some legacy mobile phone data cable. Anything will do, as long as the signal levels are 3.3 volts. Now let's see if it works. I have brought some portable power. Yeah, it's not a very nice setup, I know. Let's see if we can start this up. Maybe I should continue the talk so that we don't get too much into time problems. This is the same for a parallel drive. You can see there's a parallel ATA connector. I've done a little bridge there so that it will stay in master when I'm playing with it. And you can see the arrows, so you can try that. You just take a little USB serial thing and you plug it into your drive and you start playing. I think the slides will be published anyway after the Congress. Now, why didn't so many people stumble over it? It's just because you need a Control-Z to enter terminal diagnostics, and when you send it to the drive, then it starts talking to you. Yeah, you've got some other commands. It's just a rough overview, so I will go there more quickly. Well, some commands. You can, for instance, read some temperatures out of the drive. You can enter a new serial number. That's what I told. Well, on my slide, actually, it says Melissa on the right. Anyway, that's how I did the hack by CCC model name. I changed the corresponding stuff parameters in the system sector, so that the drive will report this model name. Yeah, and you can get some more engineering info from the drive. For instance, the zone table on the left side, and on the right-hand side, we don't have it completely, but it is the head and preamp setups for each media zone for each head. This drive only had one head because otherwise the table would be too long, so I chose one that only has one head. But it will report it for all heads it has. Well, yes, and now we can start to play with it, hopefully. And I will start to try to start the terminal. What is the time? Ooh, shit. we have to do it quick. Let's stop this. How do I stop this funny slideshow? Okay. No. I know. I have to type it here so it's faster, and I will move it over to you when I've got the terminal program fired up. Now, let's see. Maybe we can increase the font size a little bit. Better, I think. Now, hopefully it works, because you know how it is when you try to demonstrate something. I just switch on the drive, and what are we seeing? Yeah, it's booting. Nice. Now, I press Ctrl Z, and you can see we are now in the T command mode. There are several levels in the firmware which are assigned to different things that you can set or read or do with it. And the T is the main diagnostics mode. And yeah, and now you can just, we can enter the commands. First, let's say I read the third code. Yep, I read the third code. And next thing will be, let's say, now we do the serial number thing. Now, anyone to suggest a name? I will just use that one. Is it Melissa? Right, okay. No, we didn't use a packet writer. That's it. And now we write that back to the media, and now the serial number of this drive is Melissa. Unfortunately, I haven't got a second computer, so I can prove it for you that it will now report over the SATA that its serial number is Melissa, but you can trust me. Well, I think that was about it, and so I'm probably almost ready on time, and now we're open for questions.
Yes, we are. Okay, please wait for the microphone to arrive at your place. The guy in the... Yep, there we go.
One question, you told us about fire damage and what is the best way to kill a drive permanently? So if we can't burn our data or toss it in water and you will repair it, what is the best way to kill our data permanently?
That's a very difficult question, actually. I think in most cases it will be sufficient to overwrite the data once. Overwriting the data more than once doesn't make any sense. Not overwriting the data once or 10 times doesn't make any difference either. What I'm going to say is, as a normal user, you are unable to judge if you actually overwrote the data that you think you have overwritten, because there is no one-to-one relation between LBA addresses from the outside and physical addresses on the media.
Okay, thank you very much. Then we have a question from the IRC channel from our peace missions outside. Here we go.
What is the easiest and cheapest way to make a drive? Oh, sorry. I read it the wrong place. Is there some software for home users to use, and how much time does it cost?
Sorry?
No, how much? I mixed the questions. Does the heat from a fire mess with the magnetic transitions noticeably? Transitions.
Can you read that again?
Yes. Does the heat from a fire mess with the magnetic transitions noticeably?
Usually not. Usually fires are not hot enough to interfere with the magnetic recording. The Curie temperature of these media is very high. It's several hundred degrees centigrade at least.
Okay. One more question from the IRC channel. Is there some software for home users to use to interact with the drive, and how much does it cost?
You can, I mean, as I've shown you here, this was Minicom, I think. Well, it's just you can choose any terminal program. For instance, on Windows, I think they have this hyperterm or something. So there is not any cost involved to play with the drive apart from the brick drive.
Okay, thank you. One question from the back, Scoopy.
Okay. Now, the commands we've seen are not exactly intuitive, so I was just wondering how close you collaborate with the manufacturers.
Well, we would love to, but the manufacturers don't like to collaborate with us regularly, usually, with some exceptions, actually, because recently we have some partnership with some manufacturers, and well, we haven't got the real information so far, but it looks promising.
Okay, next question from up front here. Please wait for a microphone.
Is it doable to reverse the firmware of the hard drive?
Excuse me?
Is it doable?
Yeah, well, yes and no. Yeah, now I got your question. Is it easy to reverse the firmware? They are using standard processors. For instance, ARM cores are very popular also in hard drives, as they are in SSDs. So there is a chance of reversing it, but I have to tell, a modern hard drive has some 100 modules and a lot of megabytes of code and data mixed. Most of the firmware actually is recorded to the surface. So it has in its ROM, where it boots, it has sort of a boot code and a sort of initial parameters, and then it goes to the surface, and then it reads overlay modules from the surface and pulls them into RAM, and then starts them partly, and also it pulls tables into the RAM from the media, and that the whole thing is the whole firmware topic is quite complicated, but in theory it's possible. We have not. To answer your question, we have not reversed 100% of the hard drive firmware because you're getting a new model every week.
Could you repeat the question, please?
I repeat the question. How far do you need to reverse the firmware to get there? Not very deeply, because many microcontroller systems have out-of-band interfaces. That's something you know. So you will start searching for them, and you will find some hints where to find them.
Okay, thank you very much. We have one last question and one quick answer.
Hi, do you know SpinRite by Steve Gibson, and what do you think of it?
What?
SpinRite, Steve Gibson Research?
No, I don't know it, sorry.
Oh, wow, interesting.
Is that a book, a movie?
They call it the ultimate disk recovery and maintenance tool. If you listen to Security Now podcast, you will know it.
Okay, good.
Does anybody
have
know
a
it?
look.
Okay, well, the next talk is coming up and we have to clear the room now. Thank you very much for being here, Peter. Thank you for spending your time.